We are going to enter into our third presentation today of the 2021 Python Web Conference. And with me is Nelson Antonio Carrasquel from Venezuela. He's a chemical engineering professor, and he will be speaking to us about the Rackio Framework, bringing the power of Python into single board computers. With that, over to you, Nelson.
Hi, and thanks, Kim, for the introduction. So I'm glad to be here, and let's get into it. So my presentation is about the Rackio Framework. This is a technology that we built in order to create industrial applications and industrial automation. So the title is Bringing the Power of Python into SBC. So SBC here stands for single board computers. I mean, single board computers such as Raspberry Pi or BeagleBone Black, okay? So these microboard computers in which you can include any Python application. So let's get into it. Who am I? Well, my name is Nelson Antonio Carrasquel, and I'm a chemical engineer. I'm also a Python developer. It has been 5 years since I graduated from college and 10 years since I started developing in Python. And I'm also a college professor. I teach programming and chemical engineering laboratory. And for a couple of years, I have become an open source software developer. And by the way, if you're wondering, this is me. And here I'm enjoying two of the most things that I like, sushi and beers. So we can talk about that later. Okay, so what is a Rackio Framework? Rackio Framework, in short, is a modern Python framework for microboard automation and control application development. Okay, but what do you mean about this? Well, in order to understand this, we have to understand first a couple of things. First, what is automation? And this is not the common or the latest definition of automation. It's a previous one, is an older definition that is used in industry. So according to the Wikipedia, automation or automatic control includes the use of various control systems for operating equipment, such as machinery, processes, and applications with reduced human intervention. So we have another term that we might understand first, is the concept of industrial automation. So industrial automation deals primarily with the automation of manufacturing, quality control, and materials handling processes. And where can you find industrial automation? Where you can find industrial automation in the following fields. You can find industrial automation in electricity production and distribution, water supply and treatment, food production, chemical and pharmaceutical production, among other fields. There is plenty of fields, but let's keep it with the most common ones. And let's talk about a little bit of history. In this section, I'm going to talk about how we ended up building a framework for this purpose. So I'm going to start in the point where I got graduated from college, and I was working with a company that develops control system, primarily in the oil and gas field. And they develop control system for compressors and industrial turbines. And they use old-fashioned automation using Siemens and Rockwell as some of the examples. And eventually, in time, the company wanted to extend the services and the products. So they wanted to integrate into their products some artificial intelligence in order to make detections, diagnosis, or prediction of malfunctionings or failure or possible failure in some processes or machinery. So in this point, we started to wonder what technologies could we use. At the first, we were using MATLAB and we were using LabVIEW. So we were using MATLAB to train our models to detect information in data from the industry, from the factory floor, misbehavior or malfunctioning. And we were migrating this model from LabVIEW, from MATLAB into LabVIEW in order to make this an online already connected with the industry. And we got into a little bit of problems and there were rough times. So at some point, I proposed the team that we can use Python for this purpose because Python was arising as the best programming language in order to do data science. So we ended up doing some Python coding, and we migrated from MATLAB and LabVIEW to full Python. And at some point, we realized that we were doing pretty much common coding for different applications. So we thought, well, we can convert this into a library. And finally, we converted it into an open source framework. And we ended up calling Rackio because a rack is like this tiny piece that you see here behind this Raspberry Pi. And IO stands for input and output. And we ended up creating applications with this framework and deploying it in some Raspberry Pi, some industrial grade Raspberry Pi, such as this one. So industrial grade means that it can handle high temperature, high vibrations, high acoustical. So we have these requirements to meet industrial stress. Okay, so moving on. So what we came up with finally? Well, we came up with a framework that you can perform these several tasks or operations. You can do alarm detection, you can do process logic, some communication, some sensors and actuators. And upon this, we created also the capability of doing a RESTful API. And above this one, a microweb framework, something similar to Flask. We inspired all of these in other frameworks. And we centralized all of these operations on a tag engine. So analogy with the old-fashioned automation, we have a centralized data points. So we call this the tag engine, in which all of the operations can communicate through the tag engine, right? So I'm going to show you later how we can, by using Python code, can do a bunch of stuff on these functional blocks, okay? So how to do automation? Well, automation, according to Jonas Newberg in his talk in a Pi conference, he called this conference Factory Automation with Python. He explained automation using this equation. He says the actuation is the sum of sensing, actuations, and brains. So what do you mean by that? Let's take a look at this image. This image depicts the process of regulating the temperature of the shower. So you would open the hot valve, the hot water valve, and with your skin, you will sense if it is too hot or too cold. So you then open the other valve. So you start to regulate this. So you are closing the loop. So you are sensing, then you are taking some actions into account based on those inputs, and then you will regulate. So you're doing automation, but without any electronics or computers. And industrial automation is pretty much this same thing, but using electronics and computers. So I'm going to show you what Jonas Newberg in his talk demonstrated. He wanted to see how you can do Python automation by using a conveyor to organize boxes of gums into blue or red. So he used this conveyor with two paddles. And so in a way, when the gum was in the end of the conveyor, it gets dumped into the red box or the blue box. So he used this logic in here that we can see in this diagram. He has a barcode scan, so that way he can detect which box of gum was being put in the conveyor. And with some logic, he can check what is the dominant color, red or blue. And according to that, he can then toggle the left paddle or the right paddle in order to move the gum box in a way that ends up in the blue bucket or the red bucket. And this is pretty much the code that he used for that. It's just really, really short code, and it's really readable. But there is a pattern in this code that you often find in automation applications. And what is the common use pattern? Well, the common use pattern behaves or shows the following. So you have a Python code with some initializations. Then you have the code for the sensing or the data acquisition. You take some values from the real world, then you do some brains, you process some logic based on those inputs, and you ended up doing some actuations. You are reading and writing to some electrical devices that you can communicate based on any interface. You can use, for instance, in this case, he used a PLC that he can write or read values to. And you will do this in an infinite while loop, in a perpetual loop. So what is the problem with this pattern? Well, actually, in terms of execution, there is no problem. But the problem arises, and it's the problem that we often saw, is that when an application gets too complex, it's really hard to maintain this code. So we ended up doing some really long spaghetti code. So we wanted to address this problem by doing some software engineering and by following some design principles. And we met these design principles called Smores. So Smores means scalable, modular, reusable, extensible, and simple. And this is a design principle used often by the LabVIEW application developers. And we wanted to meet these principles. So we wanted also to include the common application or the common features that you find in modern applications. So what are these features? Well, you have a main features, which can be the combination of several features to meet a single purpose. You want to detect, you want to diagnose, or you want to predict something in your industry. Then you have common features, such as central data points, data logging, data history, perhaps alarming if a data point goes above or below any threshold. You want to alarm an operator. Then there is communication protocols because you might want to interconnect several interfaces inside the industry. And finally, the human-machine interface. You want to show the operators the health of the machine or the process in order they can do and they can make an informed decision. Okay. And we ended up, in this part, the main feature, we could abstract a code that you can reuse for doing pretty much the fourth above, the five above, below, sorry. But for the main feature, you can have different ways or different main features. You can have anything that you might want to code in an application. But we wanted to abstract something that you can reuse for developing a main feature in your automation application. So we took a look at how electrical engineers design systems in the past, and they used this concept called machine state. We ended up creating something really similar. Well, we wanted to create a mechanism to define system following these constraints: easy to understand, easy to develop, multi-threading, easy to extend, and easy to maintain. So we took a look at the state machine concept. That is one of the concepts that was used for electrical engineers, and today it is used also to design digital systems. And we ended up building something called Rackio state machine. And this is something that we built in order for you to create subsystem inside your application by following some design principles. So what is a state machine? First, we need to understand what is a state machine. Well, according to the Wikipedia, a state machine is a mathematical model of computation in which an abstract machine can be in exactly one of a finite number of states in any given time. So where there are other aspects we need to consider in a state machine, and are the followings. So what other characteristics does a state machines exhibit? Well, the state machine can change from one state to another in response to some inputs. This is a key point because we want to be able to do some logic according of what we are receiving in the sensors or in the data acquisitions. Then the change from one state to another is called transition. So I highlight these 3 points in here because those are the key parts of doing some automation based on the equation that we already see. All right. Okay. So moving along. So, but what is a Rackio state machine? I mean, we built this, but what is it? Well, a Rackio state machine is a base class that can be inherited to define a custom state machine with a set of states and transitions, which can be well integrated with other features in Rackio Framework. But this is just all theory. Let's take a look at an example of how we can perform automation using a Rackio state machine and including other features. Well, by the way, let me explain first how does a Rackio state machine works. Let's suppose that you have an application that has 3 main features, and each one of those is defined by a Rackio state machine. So each one of those, when the application is up and running, is going to be executing in an isolated thread. And that thread works the same way of a scheduler. It's a mix between a scheduler and an event loop. And by the time it goes, this scheduler is going to execute the current transition or the current state. So based on inputs or some behavior, you're going to trigger transitions or not. So you're going to keep executing the same state or change to another state, okay? And these boxes here has different sizes because you can execute states or transitions in different periods or different frequencies. You can define that as well. Okay, let's see now an example of such an application, such an automation in Python, or more specific in Rackio. Let's suppose we have the following. Let's suppose we want to automate the following. We want to generate an application that automatically fires a cannon continuously without allowing it to get dangerously hot. So we have, for this, to meet this purpose, we have the following. We have a cannon, we have some temperature sensors, we have a passive cooling system, an active cooling system, and a shutdown button. So if you're wondering what is this passive and active cooling system, let's suppose that the passive cooling system is just one fan, right? And the active cooling system is 3 fans. So you can cool down better something, okay? And we're gonna do a better implementation with Rackio Framework. But first, since we are doing a state machine, a Rackio state machine, we need to define the state machines to meet this purpose. So we have these state diagrams, okay? So we start by defining conceptually our application and then coding it. So initially we have first initial state, then this state goes to power up. Perhaps here you have some initializations like sensors and actuators. Then you heat up the cannon, and then you go to the main state, which is the check status. So if the cannon is okay, we can fire and we can keep firing, okay? But at some point, the cannon gets too hot or a bit hot, it goes to passive cooling. If in this process it's not cool enough, it's not cold enough, we go to an active cooling, and we go back to check status in each of these 2 states. And we can trigger a manual shutdown of if it is too hot and it's not getting cool, we just shut it down automatically. So we repeat this process of firing, checking the status, cooling it, and firing over and over. So we want this to be executed perpetuous, similar to an infinite while true. But we don't want to use an infinite while true. We want to use a Rackio state machine. So how do we do that? Well, let's code this application. And let's talk first about what would be the directory of such an application. Well, here we have the main directory, and we wanted to follow a structure similar of a structure that you would find in Flask or Django or any other framework. You could have directory. This is something called separations of concerns. You have your files for web, your files for the API. Then you have these two directories called templates and statics. So they work pretty similar to Flask. Everything that you dump in the static will be served as static files, and everything dumped in the templates you can render it in a web application. And okay, let's go. Then we have the tags and the state machines. Let's see what we can do in those modules. In the main module, we just have the importations. We import each concern. We define our Rackio application. If we want, we can set a log, and then we run the application. Pretty similar how we do it in Flask or any other web application. Then we have the tags module. Here we can define the data points in which we want to do some logic. We have the temperature tag here in the acquisition group. We have the shutdown tag for controlling the manual shutdown. And we have some parameters like the hot threshold, the too hot threshold, and the shutdown threshold. So we can define the tag engine as an API from the Rackio Framework. This API works as a singleton in which you can define tags. So you can set group of tag, and you can write default values for tags. We can rewrite these values once the application is running. So that is one of the advantages of having a centralized data point. All right, what is the kernel model? In the kernel model, we will define the Rackio state machine. So we import some models from the Rackio. We import the Rackio application, the Rackio state machines, the state class, and the group binding class. And we can define a state machines by using this decorator. We define a machine, we provide the name and the period in which we want this machine to keep executing. And this is in seconds. Each 5 seconds, the machine is going to get executed, whether it is a transition or a state. And we define the state according to the state diagram that we had in the previous image. So we have the init, the power up, the check status, the fire, the passive cooling, the active cooling, and the shutdown. So it is one state for each one of the states in the state diagram, okay? Then we have some transitions. We can define transitions by using the two methods from one transition to another. For instance, this init to power up is the init state to the power up state. So this way of defining transitions makes it more readable. So we wanted to achieve that in this coding. And okay, so how do we define the behavior of the state machine? Well, by defining method, we can customize the behavior of our state machine to meet the required automation. We do the following format. We follow the following format. If we define a method in this class on and the name of the transition, that is the code that is being triggered on a transition. If we define a method called while underscore state, and we use the name of a state, that is the code that gets executed inside an state, okay? And with this canon, we do the following. In the initialization, we just define a PLC, and we trigger the transition to the power up. Then while we're on the power up, we just transition to the check status. And in the check status is where the process logic occurs. We check if the temperature is greater to the too hot threshold, or if it's greater to the hot threshold. In each case, we trigger to the active cooling or the passive cooling. Otherwise, we just fire the cannon, okay? Then on check status to fire, this is something that happens on this transition. We set the burst counter to 0 because we want to fire 2 times, 3 times on a row before getting back to the check status, okay? And this is the code that we use while we're firing it. And since we're not checking here the temperatures can get too hot. So we can reduce the burst counter eventually. Then we have other transitions, another coding while we are on a status. For instance, while active cooling, we are turning on the fan and we're checking if the temperature reduced. So we can move back to the check status, or other case, we go to shoot down, okay? Okay, so this is pretty much, but with a passive cooling, which is pretty much the same. And finally, we have the shutdown. Okay, so wait a minute. This is a Python web conference, but what about the web? Well, we have a built-in microweb framework. So we were using Falcon framework at the beginning, and we saw that we could convert the Falcon framework uses the object-oriented paradigm. So we saw that we could convert this into decorators. So this micro framework has decorators to do basic things that you would find in Flask, such as the following. For example, we can define an API to shoot down the cannon, okay? And we can do it as following. We can import some resources, some classes to define resources, and we can use the decorator to define a route. And the route will do the following. We can define the HTTP methods, such as post and get, doing a similar way as we did with state machines. We can define what to do on a post request by defining the onPost method. So on an onPost method, for this resource, we just want to shoot down the cannon. So we can call the state machines that handles the cannon, and we could just activate this transition, active cooling to shoot down, or the check status to shoot down. That way we can tell the cannon, go to shoot down no matter what. We can also change the parameters. We can see the settings of the parameters, like the values for hot threshold to hot threshold on shoot down threshold, even the burst counter. And we can define a route for that. We can define a get method on this route using an object-oriented approach. And we can define a post method for this same one, just in case we want to change the values of these parameters. We want to increase the hot thresholds, just in case we are in a really cold country. Or we can increase the burst counter. We want to shoot more or shoot less. And we can use any of the features. In this case, we're using the tag engine. By the way, every time you inherit a class from Rackio, you will have all of the common services included. So the tag engine is by default in a parameter called tag engine. And what about the web? Well, we took the object-oriented approach and converted into decorators. So we can define routes, web routes, by using a similar approach that you can find in Flask. You can define a route, and you can render some HTML in this rendering. You can use templates that you save in your templates directory, pretty much as you would do in Flask. But what about the hardware architecture? So let's talk a little bit about hardware architecture. Once you already have your application, how do you deploy it? Well, you can include this application in any Linux board and put it in the industry. You can use a laptop, you can use a computer, a PC, but we started using this Raspberry Pi industrial grade. This industrial grade Raspberry Pi. So we put there our application. Since Raspberry Pi run Linux, we could root Python, and then we could root Rackio applications. So you could connect using libraries like GPIO libraries and any others to connect with sensors. You can connect through Ethernet to any TCP/IP communication protocol or RS-232. You can connect to actuators through PLCs. You can connect to databases and even to the cloud using IoT protocols. And finally, you can connect through the Ethernet cable, and you can define an HMI using the API and the web micro framework to create your own custom HMI. And by using a browser, you can connect to the IP address of this application, of this Raspberry Pi, and see your interface, the one that you have developed to monitor and check the health of your application and your process or machinery. And so what's next for Rackio Framework? Well, we want to improve its coding. This is a work in progress, and we have included a lot of effort in it. We want to include more features, or we want to include more tools so you can define custom systems. And the actor framework is another mathematical concept that we want to include in Rackio. We want to improve the authentication and the authorization, because you have this industrial application and such a small group of persons can access to this application. We want to create a MicroPython equivalent or a library for MicroPython, or perhaps in the future, we can fork MicroPython and call this MicroRackio or RackioPython. So we want to develop something that is already customized and improved for doing these single board computers applications, okay? So that's it. That was my talk, and thank you very much.